we continue with the material we started in the first part. And in the first part, we were looking at drift. That is, if you have an electric field and you have a charge in the electric field, then we discussed how this charge moves on the electric field. Uh, then we extrapolated that and we looked at a semiconductor piece where we have concentration of free carriers. And then we discussed how these carriers move in response to an applied electric field. All of that we call drift, and we discussed our first device, electronic device, if you like, which is the resistor. And in a resistor, the mechanism of charge transport is mainly via drift. And then we define parameters like the mobility and conductivity and the interrelations between mobility and conductivity. I showed you how to engineer a resistor. In other words, how to make a resistor at different resistivity levels by engineering the concentration of free carriers and so on. So that concludes the resistor structure. We also talked a little bit about how to fabricate it, how to make it. Now, we want to look at a slightly modified scenario, if you like. We want to look at drift also, and that drift is also going to be in an electric field. Okay, but then in addition to that, we were going to put a magnetic field. So there'll be two fields, an electric and a magnetic field, and we see what happens. The outcome is what we call the Hall effect. And you probably heard about the Hall effect. It's a very important effect, which is utilized in so many applications. So far, we said if we have an N-type semiconductor, let's assume we have an N-type semiconductor. And in this N-type semiconductor, we will have free electrons. And if we apply an electric field, okay, in the application of an electric field, no magnetic field yet, the electron will have a velocity v sub n, n for negative for the electron. This velocity is equal to the mobility times the electric field. Okay, so the mobility is essentially the velocity per unit electric field. Okay, the magnitude of the velocity per unit electric field. Then now, if we apply a magnetic field on top of the electric field, so we have both fields, magnetic and electric, then we have learned in electromagnetic theory and electromagnetic interactions that there is a magnetic force, Fm, also on the electron. Electron is a charged particle. And this magnetic force is only effective when the charge is moving. In other words, if you have a charge at rest, no force acting on this charge because of the applied magnetic field. However, as soon as this charge starts moving, then there is a force. This force is this Fm force, or the magnetic force. And this magnetic force is called Lorentz force. Lorentz, after the scientist or the physicist who first observed this force, okay? And so this Lorentz force is the force that results from the magnetic field, okay? And this force is proportional to the magnitude of the charge. The more charge you have, the more force you have. as well as the velocity. We said that this charge has to be moving. So the larger the velocity of the charge, the larger the force, the magnetic force, and also the magnetic field. The larger the magnetic field, the larger the magnetic force. So it depends on the charge, on the velocity, as well as on the magnetic field. More importantly, however, this magnetic force happens in a direction perpendicular to the plane containing the field and the velocity vector. So it happens in a plane perpendicular to the plane of magnetic field and the velocity, okay, which is somewhat different from the electric force. The electric force is in the same direction as the electric field. Here, the magnetic force is perpendicular to the magnetic field. So it is a different force. Okay. Now, let's think of this experiment. Let's think of a semiconductor here. We take a piece which is semiconducting. Let's assume that this semiconductor is n-type, so it has electrons, free electrons. Of course, in a semiconductor, you have also holes, but you also have ions. Remember, we said n-type, meaning that you have maybe phosphorus dopants or donors, and those phosphorus donors have donated their electrons, right? And therefore they become positively charged ions. So we have positive charge, which is the ions, all these phosphorus. We also have the electrons that came from these phosphorus atoms that are free moving. And then the net effect is that the negative charge on the electron and the positive charge on the ions are exactly equal. And therefore, the n-type semiconductor is neutral, but it has free electrons moving. Okay, so let's have such a semiconductor, n-type, connected to a battery, as we see here. We see the two poles of the battery, plus and minus. So this side here of the semiconductor is connected to the positive, okay, positive pole of the battery. And the backside here is connected to the negative pole. So what happens is the electrons would move from this side to this side. Then we can imagine that any positive charge would move from this side to this side following the magnetic field. So the magnetic field would be in this direction. This is the direction of the magnetic field from the battery, right? Okay, so this is the magnetic field coming from the battery, and therefore the positive charge, okay, or what we imagine to be positive charge in this, will be moving in this direction. Okay? Okay, now before I discuss this more, let me just take you to the next slide. The next slide is a mathematical relationship which gives me the force, the magnetic force on a charge. Okay, now this charge is an electron. Look here, it's minus E. So the charge is a negative charge in the electron, and that's why we have negative here. Okay, so the negative meaning negative charge. And then we have V, the velocity, cross B. So we have a cross product. Two vectors, V and B, in a cross product. And if you have two vectors in a cross product, the result is a vector perpendicular to the two vectors. But they form a right-handed system. That is to say, if we draw, coordinate system like this, okay, then if this is V, okay, this is V, and this would be F. So you see that F is perpendicular to the plane of V and B, right? Making 90 degrees with both V and B. And it's a right-handed system. So if I hold my right hand and the thumb points in the direction of V, and the first finger points in the direction of B, then the second finger will point in the direction of F. So the force is perpendicular to V and B. And it depends on V. The magnitude depends on the magnitude of V and the magnitude of B, as well as the charge E. So that's what we said before. So let's go back here. This is the velocity in this direction of the positive charge. The magnetic field here, and I'm showing it as a cross, meaning cross is a back of an arrow. So I'm thinking of an arrow going this way. This is not drawn very well. So I'm thinking of an arrow, maybe here in this direction, okay, going into the paper, into the slide. So the bottom or the back of the arrow, which is what I'm showing here, is the cross of the arrow, the tail of the arrow. Okay, so the tail of the arrow is the cross, and the tip or the head of the arrow is going into the slide, into the paper, into the view graph. So now, if this is V and this is B, then the force would be perpendicular. So what you have here is this is your B, this is your V, okay, this is V, this is your B going into the paper, and so your Lorentz force would be perpendicular, F, okay, and it's a right-handed system. If you hold your right hand and point towards V with your thumb, and your B with your first hand, with your first finger, then your second finger will point towards in the direction of F, meaning that the three fingers are held mutually perpendicular to one another. So this would be the force on a positive charge, right? Oh, sorry, I made a mistake here. Pardon me. If we do it all right, the right hand rule right, actually the force would be apparently I draw it right. The force would be down here. Okay, so that means the force will be pointing down, and so the force on a positive charge will point down. And so in this case, what we will have is the positive charge deflected towards the bottom of the semiconductor, the bottom face. The electrons that are negatively charged, opposite charge, will be deflected to the top. Okay, because the Lorentz force is perpendicular both to V and B. So what you will get is negative charge, negative electrons near the top face, and the positive charge more to the bottom face. Now, we know that the positive charge is ions. Ions do not move. So what actually has moved are these free electrons. So they moved away from the bottom face to the top face. And when they move to the top face, away from the bottom face, what is left in the bottom face of the semiconductor is positive charge. So essentially, you have positive charge on the bottom half of the semiconductor or bottom face, and negative charge in the top face. And if you have positive and negative charge in a semiconductor, you immediately have an electric field between the positive and negative charge. And here you see it. The electric field, which I'm calling E sub H, and we will know why we are using H. First of all, this E sub H is different from this E. This E comes from the battery. This E sub H comes from the motion of the electrons and holes, electrons and positive charge on the two faces. So what you have is, because you have a drift of electrons here in this electric field and magnetic field, you generate an electric field perpendicular to the applied electric field, applied meaning applied by the battery, and perpendicular to the direction of motion of the charge. Okay? And so because of this accumulation of charge in the two faces, one or the charge creates an electric field, which is EH. This EH is called the Hall electric field. So EH is Hall electric field. And Hall is a British scientist who actually observed, this effect, Hall electric field. So because of the motion of a charge or in a magnetic field, in a semiconductor, this electric field, which we call Hall electric field, happens in a direction perpendicular to the applied electric field and perpendicular to the motion of the charge in the semiconductor. And we know that an electric field gives rise to a potential. So that means if I connect the top and bottom electrodes, I will get a potential difference between the two because they have accumulation of charge on the two faces, just like a battery. A battery is a positive plate and a negative plate. And because of that, you get a potential difference or electromotive force or a driving potential between these two terminals. So our VH here, this VH is actually what we call the Hall voltage. Okay, so now the essence of this experiment is I have a piece of a semiconductor. Okay, I put this piece of I connect it to a battery. Okay, and then I pass a current through this piece of a semiconductor, but I have it placed in a magnetic field, B, and because of this, I get an electric field or a Hall voltage across two opposite faces of this semiconductor. This voltage is called Hall voltage, and I can actually measure this Hall voltage. Okay, so what's the outcome of this experiment? How do I make use of this experiment? Okay, now this here is the equation, that governs everything. Now, if I have V perpendicular to B, like if I have V in the X direction and B is in the Y direction, then F is in the Z direction. And I can neglect the V, the vector notation, but just think of it as V is moving in the X direction, B, the applied magnetic field is in the Y direction, and therefore the Lorentz force, V, F is in the Z direction. Okay, so so this is the rule that we actually use. Now let's go to this page then. So the magnitude of the Lorentz force F is E times speed times B. Let's now think of the three dimensions X, Y, and Z, just to make it simple. So we know force in the Z direction, V is in the X direction, B is in the Y direction. So the magnitude of the force is simply E times V times B. Okay, this is the force that acts on a charge and deflects it to the top plate or the bottom plate. So this is my force here, EVB. That's the FM, the Lorentz force. Okay, now the question is, does this continue forever? Okay, the answer is simple. And if we go back to this figure, now we have an electric field, right, happening when you get the deflection of charge like this. As more and more charge moves, again, the positive charge deflects here and the electrons deflect up. But look, I already have an electric field EH. Now, this electric field EH is in such a way that if an electron wants to go up here, this electric field, which is now produced, opposes the motion of the electron to the top plate, because the electron would be moving in the direction of this electric field EH if it wants to move to the top plate. And that cannot happen. The electron would have to move opposite to the direction of the electric field. So actually, this electric field that is produced would oppose the motion of the electron, right? Makes it difficult. So what I'm implying here is that there will come a time when you get equilibrium. No more electrons are able to go to the top surface because of this electric field. So this electric field should produce an opposing force exactly opposing to Lorentz force, or the magnetic force, which is trying to push the electrons to the top. In equilibrium, they have to be equal, okay? And that is what you have here. If you have a whole electric field EH and you have electron charge E, then the force on the electron from this whole field is EH. And this force would have to be exactly equal to the Lorentz force so that we get equilibrium. So we can set, in equilibrium, we can set these two equal to one another, and that helps us get, the electric field. Because I know the applied magnetic field, I know that maybe the velocity of the electron, then I would know what kind of whole field would be produced. But again, if I go back to this drawing here, and if I assume that the thickness of this semiconductor sample is H, so this is H, right? This is the thickness here. This thickness is H. And the potential of the whole voltage produced is VH. And that whole voltage is produced from an electric field EH. Then I know that VH and EH are related. In fact, EH is simply equal to VH over H. Okay, and that is what